WWT presents Briefings.
Hi, my name is Phillip Hendrickson. I'm a solutions architect at Worldwide Technology. I've been here for just under a year, but I've been in the HPC and AI and solutions architecture space for the better part of 20 years. I have a PhD. My PhD is in computational neuroscience, and in the early 2000s, I was building large-scale biological neural networks, and that required traditional high-performance computing infrastructure to run at the scale that I was running at. And so as a graduate student, I started by architecting a fairly large-scale high-performance compute cluster, and then I spent the rest of my graduate work actually building the models, validating the models, testing the models, parallelizing the models, getting them to perform well. And along the way, I generated a ton of data and had to learn how to do the data analytics and the data visualization, and then explain it to a bunch of people who didn't care about the hardware and the technical issues that I went through. Since then, I've been at small organizations. I've been at very large organizations. I've worked in government spaces, and now I'm at Worldwide Technology. I have experience in, as I said, in high performance and complex systems architecture, I think at a systems level. But I also understand the workloads, and in the generative AI world that we live in today, I have a kind of a unique capability to talk to both data scientists, data analysts, and IT and facilities folks. That's my background. My goal here is to talk about how we think about how we at Worldwide Technology and how I and my team think about sizing and architecture principles for a given generative AI or non-generative AI workload. The assumptions that we come into for this principle-based methodology or this principle-based process is that we're going to be talking to a business executive or a project manager or a facilities person or an IT person or even a data scientist. They know their business, they know their user base, they know what their business goal is, they know what they're trying to accomplish. They want to stand up an AI application, whether it's a generative AI or a more traditional ML non-generative model. And they oftentimes know what the application requirements are. And what they want to know is what kind of hardware and infrastructure and software and middleware do they need in order to support that particular workload, and how much of it do they need. We don't see that all the way across the board. We see some business owners who want to start with the infrastructure and they figure out later how much or what they're going to run on it and how much it's going to cost and how much power it's going to take. But we see a lot of folks who know what they want to run and they want to match the infrastructure to that particular workload with some room for growth. When I started at Worldwide a little under a year ago, I came in asking questions about that. How do we think about sizing? How do we think about architecture? How do we think about matching the architecture and the infrastructure to the particular use case, the particular set of use cases? And pretty quickly we realized that we needed to do some work in that area. And so I set about over the last 6 months to 8 months, I've spent a bunch of time working on how we can do that. In order to size the infrastructure to a particular ML workload, you need a principle-based approach, and you need to pair it with collecting actual data from a performance perspective. And let me explain both of these. From a principle-based approach, you need to understand how generative models and how neural networks run, how the algorithms work. And from that, you can determine what sorts of parameters are going to affect performance. I'll explain all of this. So if you look at the image or the diagram at the bottom of the slide, let's say that I'm a user, I go on to ChatGPT and I want to ask a question. I type in a response into the box, and I click enter. Go process this and give me a response back. What happens behind the scene is a very complex set of processes and algorithms. First of all, neural networks don't understand English. They don't understand Spanish. They don't understand human spoken language. They're generative models for protein sequences. These models don't understand protein sequences. What they understand is very high-dimensional math and high-dimensional vectors. If you think 2D or if you think 3D, that's 2 dimensions, 3 dimensions. These neural networks operate in hundreds or thousands of dimensions. And there's a whole branch of computer science dedicated to converting human language or weather patterns, weather data, weather patterns, or protein sequences or drug sequences into this high-dimensional space. That process is called vectorization or tokenization. And so I, as a user of ChatGPT, just entered my query. That query gets broken down into a bunch of little bits, and all of those bits get vectorized. All of those vectors then get submitted to the neural network simultaneously. That's what is represented by all of those arrows going into the generative model. Computing a generative model is a very computationally intense task. It's a bunch of matrix math. For the computer science majors out there, you're doing a bunch of matrix multiplies, which is a bunch of addition and multiplications across a very large dimensional space. And it requires a lot of compute, and it requires a lot of memory bandwidth. And what comes out of that neural network traversal? A single token, or a few letters of a single word comes out of that. Well, I need more than a single token because the response that's going to come back is probably going to be tens or hundreds or maybe thousands of words. Single token comes out, and so in order to produce a second token, you need to produce a second token and a third token and a fourth token and a fifth token. The way those get produced is through it's what's called autoregression. Single token gets added to the original input. So now if I had 10 tokens going in, now I have an 11th token. 11 tokens get resubmitted to the neural network, and the neural network gets traversed again completely to produce a second token. Second token gets added. Now there are 12 tokens. It gets submitted, traverses the entire neural network a third time, and continue. If I want 100 tokens, I traverse the neural network 100 times. And at the end of that, I have 100 tokens, represents 80 or 90 words or whatever it happens to be. Those all get decoded, turned back into English or turned back into Spanish or turned back into whatever language it is that that I want to read the response in, and that gets fed back to me. So there's a time component here. A single token gets produced in a given amount of time, and 100 tokens get produced in 100 times that amount of time. 1,000 tokens get produced in 1,000 times that amount of time. What affects performance? What affects the time that it takes to produce that single token and the second token and the third token? Well, there are a number of things. The size of the model matters. Models, you've heard of Llama 2, you've heard of Llama 3, you've heard of GPT 3 and 4 and 01, and there are a bunch of models, a large proliferation of models. And we talk about these models in terms of the number of billions or trillions of parameters. So the size of the model matters. A billion parameter model takes it takes a certain amount of memory and requires a certain amount of memory bandwidth to move all of that data into the compute. It requires a certain amount of compute to actually do the matrix math. A 10 billion parameter token or 10 billion parameter model requires 10 times that amount of memory and 10 times the bandwidth and 10 times the compute. A 100 billion parameter model requires 100 times that, and you can see how that scales.
Today's episode is brought to you by Equinix, powering innovation for today and tomorrow. Equinix provides the global reach, the rich ecosystem, and the service excellence today's organizations need to compete and win.
Other things that matter here are the token count. If I'm producing 10 tokens, that requires a certain amount of time. If I'm producing 100 tokens, that requires 10 times the amount of time. 1,000 tokens requires 100 times the amount of time, which is, again, a fairly simple to describe scaling model here. What else affects performance? Well, the volume of requests. If I have a single user on a system asking it for things, that's very different than if I have 10 users or 1,000 users or 10,000 users or 100,000 users who are all submitting requests at the same amount of time. That's very nonlinear. It's not linear at all. And I'll talk a little bit more about how we look at that nonlinearity in just a minute. A lot of applications are not just user entering requests and that request being forwarded to a large language model. If you've heard of RAG, RAG is kind of table stakes at this point for a lot of businesses who are building generative models. They want to add their own data to these requests and pull that data back. And so the amount of data that's sitting on storage matters. How much data is there, and how many requests, and how much data per request, and how long does the query for the data that's sitting in the database take? All of these things matter, which affect the performance of the storage and affect the performance of the network that attaches the storage to the compute. If you have really large models that don't fit in a single GPU or in a single server, they span multiple GPUs, they span multiple servers, well, then the storage or the network between the nodes matters, and the speed at which data can traverse one node to another node matters a lot. So there are a lot of factors here that affect performance. Those are just some of the principles of the principles behind how these generative models work, and those are some of the factors that affect performance. Now, we didn't want to put together the capability to do sizing based just on a principle-based approach. We wanted to actually go record data. And so you've probably heard of the Advanced Technology Center. It's a kind of a core differentiator of worldwide technology. A little under a year ago, Jim Kavanaugh announced $50 million or $500 million spend on AI-related stuff for the next 3 years, and we've started to build what's called the AI Proving Ground. We have a bunch of hardware in the AI Proving Ground: compute, networking, storage from a number of different OEMs and a number of different partners, along with the software sitting on top of that. I've used the AI Proving Ground to really beneficial ends over the last 8 months, actually recording performance off of these various models, systematically traversing the parameter space that I just talked about across model size and across token count and across number of tokens per request and across concurrent requests. We've done it on a bunch of different NVIDIA accelerators, think A100, H100, L40S. We've done it on accelerators from Intel, Gaudi 1, Gaudi 2 CPUs. We have AMD accelerators coming in that we're going to have data from very shortly. We've done it on language models from 100 million parameters, think BERT, to 200 billion parameters. And in the last couple of months since Llama 3.1 came out, we now have a 405 billion parameter model that I get to go look at. That's going to be fun. What has come out of that, from that data plus the principles, is the ability to recommend accelerators and tell customers or tell internal folks which accelerators to buy and how many to buy based on application requirements like latency, throughput, and concurrency. There are a couple of screenshots here that I like to talk through. This sizing tool we have in a proof of concept form, and we've used it in a number of customer engagements to date. I want to walk through a couple of these just to talk about why it's so, to illustrate why it's so useful. So if you look at the top right here, we give it, let's say we have someone come to us and we say, we have a generative model that we want to build, a generative-based application that we want to build. We know that we're running a 7 billion parameter model. We need 15 tokens a second. It's not super slow, but it's not super fast. And the responses that are going to come back are not super long, 100 tokens, which is like 70 or 80 words, English language words. And we don't have a ton of concurrency. We have 1,000 users, and at the rate at which they're building these queries and making these requests, that translates into 30 peak queries per second. If you look just at the A100 The full tool lists more accelerators here, but keep this simple. This can run on the A100, NVIDIA's A100 40 gigabyte accelerator. And you can see here that the number of accelerators that we would need to meet those application requirements is 1. You could fit one of these into a 1U or a 2U server sitting in your data center. Doesn't pull a lot of power, doesn't take a lot of space. Great. And it actually gives you some room to build a couple of additional use cases if you want to, if they're a similar size. Let's say that another customer comes in with a different use case. They say, well, we don't need a 7 billion parameter model. We need a 13 billion parameter model, which is going to take more memory and require more compute. And we need this to be fairly responsive. We have very quick users coming back. They're very quick readers, and we need 25 tokens per second peak coming, or minimum coming back here. And the responses are going to be longer, 500 tokens per query. That's a decent, 2 or 3 paragraphs worth of response. Let's say that the responses are coming out of manuals, user guides, data sheets, for example, off of a RAG-based application. And we have a lot of users, right? This is both for internal use, employee use, but it's also public facing. We expect 5,000 queries per second peak, not across all 24 hours a day, but at peak traffic periods during the day, we expect 5,000 queries per second, and the infrastructure needs to support that. Well, the A100 can still support that. It can support the base latency requirements and the base tokens per query requirement. But now instead of 1 accelerator to do that, you need more than 8,000 accelerators to do that. That's something like, if you put 8 of these in a server, an older generation DGX server, that's like 1,000 DGX nodes. That's going to take a ton of rack space. It's going to require a ton of power. You're going to have to figure out how to cool it. Very big difference between 1 accelerator and 8,000 accelerators, without much change in the requirements around the application. And so this, I think, we've seen. I think that this resonates, and it's a fairly compelling example about how customers who are somewhat risk averse, customers and partners and users who are somewhat risk averse, they don't want to just buy infrastructure without knowing that the infrastructure has been sized for the particular application and the particular LLM that they're running. The caveat here that I'll add is that everything that I've said here focuses on inference for language models. We can do the same thing. We can go through the same exercise, and we have similar methodology and can help with sizing for non-language models. So if you're doing computer vision, or if you're doing other types of simple neural networks rather than generative neural networks, the exercise and the methodology becomes simpler. There are fewer parameters that affect performance. If you're wanting to fine-tune a model, well, then you get into questions about the hyperparameters for the fine-tuning and what your requirements are around time to converge, right? That's going to affect the amount of compute, and it's going to affect the networking piece of this. And if you want to train a foundational model, not a lot of folks are doing that, but some are. If you want to train a foundational model, then the entire equation becomes, and the amount of infrastructure goes up by an order of magnitude or 2, just because of how long it takes to actually do the training. Thanks for the time. Again, my name is Phillip Hendrickson. I appreciate the opportunity to talk to you about our expertise in sizing and architecture. If you have a workload or an application, an AI-based application that you're trying to size infrastructure for, we invite you to talk to one of our account managers or talk to the account manager assigned to you. They would love to come talk to you. They know our team really well, and they'll pull us in on an as-needed basis. We'd love to come help you with your problem. Thank you.